Welcome to Calculus. I'm going to walk us through the latter part of section 3.2, particularly the mean value theorem. But to introduce it, let me give you a little bit of an example. Let's say you're going on a trip, and on this trip you pass mile marker 57 at a certain time. You pass a police car going 70 miles per hour at this point. An hour and a half later, you pass mile marker 177, and again you're going 70 miles per hour. And that took 90 minutes. So were we always going 70 miles per hour? These are the mile markers again, so I can say miles. Were we always going 70 miles per hour? Well, we can find the average speed, right? So let's see, the average speed, miles per hour. How many miles did we go? Well, let's see, we covered, it appears, 120 miles in 90 minutes, which is 1.5 hours. So put 1.5 down there, so it's 120 divided by 1.5. And it appears that's 80. We averaged 80 miles an hour. Now, could you have a case? Could you say, no, officer, I never exceeded 70. You saw me at 70 at the 57 mile marker. You saw me at 70, or someone else did at the 157. I was going 70 the whole time. Well, of course, no, you had to go faster than 70 if your average was 80. It's kind of like if you got a 70 on your first test and a 70 on your last test, but your overall average was an 80. You must have got some grades above 70. In fact, they must have been over 80 to pull you up. But speed is different than grades, because grades would be not continuous. You can go from a 70 to 100 without getting a 71 or 72 or all the numbers in between. But with speed it's different. So since your average speed was 80, we probably instinctively know that you were going 70 sometimes, you were going over 80 at sometimes, and there must actually, speed is continuous, so you must have hit every number. 75, you must have been going 80 at some point, you must have been going 81. Every value, it's kind of like height, like we talked about the intermediate value theorem. You can't, when you grow, you hit every value as you get taller. So what we're saying here is that if your average speed was 80, then there must have been an instant where you're going exactly 80. You could have been going greater than or less than, but again, assuming it's a continuous change in speed, there must have been an instant, at least one, probably multiple, when you're going 80. And this is the idea theorem. It's a pretty awesome theorem. In fact, if you look in the book, on page 174, in the second and last paragraph, they make this statement, that some consider this to be the most important theorem in calculus. Wow, it deserves a few exclamation marks. I don't know if we'll be that impressed, or if you'll be that impressed, but pretty important theorem. I'm not going to write it up fully here, so you can look in the book. I will read it to you, and you can write it if you want. But it says this, the mean value theorem. It says that a couple conditions are the same as the Rolle's theorem, that f must be continuous on the closed interval AB. Alright, I'll write it. F is continuous on the closed interval AB. That's a condition. And another condition is, I guess I should say, and differentiable on the open interval from A to B. Then, if those are both true, then there exists a number C. Alright, I'll write it down. Then there exists a number C in AB such that, I'll use this again for such that, the derivative of f evaluated at C is the same thing. Before I said it was 0, but now we're going to say this. See if this looks familiar to you. That's the slope formula. The change in y, that's basically y at b minus y at a divided by, this really is a change in y over change in x. So it's saying the new color here, it's saying this is the average, if you can read that, average slope must equal the instantaneous slope. Instant slope. Or I should say it this way, the instantaneous slope must equal the average slope, at least at one place. Let me show you that. Let's see it on a graph. So if this were your curve, and you're looking at it from, I don't know, here to here, and you say, what is the average slope from this A to B? Well, whatever the slope of this line is. That means since this curve here, f of x, is continuous and differentiable between A and B, then there must be a value on it where the slope is the same, and it appears somewhere around here. If I would have graphed the tangent line, it appears to be parallel somewhere around there, but there is at least one place, and that's what the mean value theorem says. Well, let's do 2 examples. May not finish these in this video, but the first one I'm going to do is actually from your book. It's number 38. Not one I assigned on the homework, but similar to, it's really bad, 38. 38, and it says this. You have a function, negative x squared, negative x squared minus x minus 6. Make that plus 6. Negative x squared minus x plus 6. And you're looking at it from negative 2 to 2. Negative 2 to 2. And you're going to say that if you were to graph that, then the slope of the secant line, I wish I had in front of me what this graph looks like. I'm not totally sure. I'm just going to guess. It looks like this. I don't know. I do know the y-intercept is 6. But anyway, from negative 2 to 2, say that's here to here. I don't know. That slope, there must be an instant where this f of x graph has that exact slope. Okay, so the first thing we're going to do this in 3 steps. Part A, the book mentions, they say, what is the exact slope of this secant line? Well, if I follow the formula, I would do the slope, we know, is change in y over change in x. So the change in y would be the difference in your y's about when x is evaluated at 2 and negative 2 minus that. So what is f at 2? It is, let's see, it is 0. F at negative 2 is negative 4. Get those backwards. 2 goes with 0. No, that's right. So f at 2 is indeed 0. Yes, that's right. And f at negative 2 is negative 4. Okay. No, positive 4. Okay. That looks better. And then this down here is going to be 2 plus 2, so we end up with negative 4 over 4, or negative 1. So, it asks you to do the equation line on this problem. I'm just going to go with negative 1 for now. So part B says, where on this graph here where is its slope? -1. So this is a little more basic. We take the derivative, and we get -2x minus 1. Wow, this is messy, sorry. So you set that equal to this slope. So -1 equals -2x minus 1. Or add 1 to both sides, you get 0. And you get x is 0. So when they're saying x, they mean that is that c value. C equals 0. When c is 0, the slope of f at x equals -1. Now part C does go on to say write the equation of the line. Erase this. Write the equation of the line. So let's try that. So first thing I need to do is say, to write the equation of the line, you need two things. You need the point, or a point, and the slope. So let's find a point. When you put in 0, you get 6. So 0, 6 is on the graph, and we want a slope of -1. So we used to use our point slope. Y minus 6 equals -1 x minus 0, or in other words, y minus 6 equals -x, or y equals -6x plus 6. So that would be the equation of the line at the tangent line point. So when x is 0, it has a slope of -1, and at that point this would be the line equation. Let's do one more. Okay, I can fit this in 3 minutes. I'm going to do number 42. This one's a little simpler. It says, here's your function. And let's check it out from 1/2 to 2. So this one, if I were to graph it, do I really want to graph this? -1 and 0. It's going to look like this, I believe. But we're not too interested in that right now. So from 1/2 to 2, you can kind of see what is that going to look like. Something like that. So we want to figure out what is the slope there. Looks negative at least. Let's find the slope. So the average slope, again, would be f at 2 minus f at 1/2 over 2 minus 1/2. Well, I'll just tell you, f at 2 is 3/2, and f at 1/2 is 3. You can check me on that. Over 2 minus 1/2, which is 3/2. And do a little bit of algebra work, and you can just trust me, this becomes -1, or you can test it out if you want. So the question then becomes, where is the slope of this? -1. So let's figure it out. Let's take the derivative. It becomes denominator, derivative of the numerator, minus numerator, derivative of the denominator. This is really unfortunate that I'm running into this. All over denominator squared. That becomes x, I'm going to distribute minus x minus 1 all over x squared, or in other words, -1 over x squared. So what we want to do is set that equal to the slope. And remember, in the Rolle's theorem is always 1, but now it's -1. So if you multiply both sides by x squared, you get -x squared equals -1, or x squared equals 1, or x is plus or minus 1. Is one of those fall in this range here of 1 to 2? Yes, and it's 1. So that is our answer. That is the number guaranteed by mean value theorem. The number that, and you can look here, that right around there, maybe the slope is exactly the same as the average slope. The instantaneous slope equals the average slope. So I hope that helps. Give it a try. Mean value theorem. Basically, you're taking the derivative and setting it equal to the average slope. The instantaneous slope equals the average slope. Hope that helps. See you next time.